The weather in this area is very dynamic.
The way that pollution impacts extreme weather conditions is extremely complicated, and we don't really fully understand it, which is why we're out here in the first place.
We're trying to investigate this in one of the most complex meteorological regimes in the world, that is around the South China Sea and Western Pacific.
We'll start with 2, check in on 2 at select start 2.
Roger, 2 is selected. Airs at 45, here we go 2.
Rotation.
The largest uncertainty that we have right now in climate forcing is the relationship of aerosol particles on cloud systems.
In Southeast Asia, 2 of the biggest sources of pollution are pollution from various sorts of cities like Metro Manila. 20 million people live there. The other really important source of pollution in this area is from biomass burning.
And what's really interesting in this region is that we have both. We both have this anthropogenic pollution as well as this biomass burning pollution.
So this is really sort of ground central for weather observations and weather and climate modeling for Earth system science.
For tower, 118.7, roger that, and we are good to go. 80 knots. Rotate.
So in this region, there's a monsoon season that happens every year, and you have this evaporative process of water vapor from the ocean. And as that water vapor cools and condenses as it gets lifted up, you form clouds.
After they turn into clouds, processes happen inside the cloud to collide the different cloud droplets together and eventually make droplets that are big enough to rain out of the clouds. And that rain goes back into the ocean and completes the water cycle.
One of the long-standing hypotheses that have been in the scientific community that pollution emissions, whether it's from cities, shipping, or biomass burning or deforestation, can affect the climate. And in particular, there's concern in the scientific community that these emissions can affect clouds.
So in order for the cloud to actually be formed, for water to be able to condense, it needs something to condense onto. So we call those cloud nuclei. And those cloud nuclei are basically can be sea salt, it can be particles from trees or from dust, or it can be particles coming from human pollution.
So the other particles that water can condense around are aerosols, and these can be in the form of anthropogenic, human-made aerosols, or biomass burning, which can also be induced by human activity, from farmers burning their fields, but also natural sources such as fires.
If you bring more particles to the environment, you get more cloud droplets. That changes the distribution of cloud droplets. That changes precipitation processes.
So aerosol and cloud interactions have been studied for a decent amount of time now, and what's really important with the aerosol and cloud interactions is that the more aerosols that you have interacting with clouds increases the number of cloud droplets.
So if there's a lot of really small droplets compared to a few bigger droplets, we think it's actually harder for the cloud to make rain.
But it can also change the reflectivity of the cloud, or albedo, which then in turn looks at a bigger picture of changing the heat balance within the local area near the Philippines and the tropics, and then in the grand picture, across the globe.
Yeah, it's a really complicated balance when you add particles to a cloud to understand how that actually affects the climate system as a whole.
There have been many studies in the region that have linked the presence of pollution and smoke particles to more severe weather. In particular, lightning activity has been shown to increase in regions under the influence of pollutants.
So understanding, as we add more particles to the atmosphere, how that changes the properties of the clouds, how that changes the properties of the storm systems, and how that changes the extreme weather that results from those storm systems is really important, and is one of the things that we're really trying to get at with this field campaign.
The waters around Southeast Asia can at times exhibit some of the cleanest atmospheres on the planet. But at the same time, throughout Southeast Asia, you have megacities such as Metro Manila, Kuala Lumpur, Jakarta, and Singapore that all emit aerosol particles into the region.
Metro Manila is one of the biggest, largest, fastest growing megacity in the region. That means, therefore, that there's a lot of development that emits pollution. And one of those is transport.
And these aerosols are different from what we find in pristine areas. And this difference has important implications on clouds and precipitation formation in this area.
The monsoonal flows of Southeast Asia bring all of these pollutants together up the South China Sea into the Philippines and to the Western Pacific.
So therefore, during this season, there are a lot of interactions that can happen with the pollution and the meteorological conditions.
And one of the primary reasons why the CAMPEX mission is centered here in the Philippines is that we can see this transition from very polluted environments to the south to the much cleaner environments to the Western Pacific.
So, at least in the Philippines, it's very important because we are often affected by a lot of extreme weather events. And by extreme weather, that can mean sometimes no rain or very intense rain. And that affects our water resources for agriculture, for our daily living, for taking a bath. So all these basic activities are very reliant on having these resources.
One of the hypotheses that started the whole CAMPEX mission was that farmers in Mindanao had noticed that the droughts have been longer, but when rain does come, it becomes more severe. One of the science objectives of this mission is to investigate, is our aerosol particles part of the cause of that?
So the measurements, therefore, from this field campaign will input into how we are running our models. For now, models that are run for weather forecasting over Metro Manila or for other places in the Philippines, for that matter, do not take into account pollution.
So it's very important to study the interactions between meteorology and pollution because we rely on it so much.
This campaign is the first step towards incorporating measurements and observations into our model and try to see whether these aerosol particles are significantly or are going to significantly impact rainfall formation.
So what's really interesting about CAMPEX is this region of the world is really hard to study just using remote sensing or satellites.
You have thunderstorms forming over the mountains, you have tropical cyclones or other tropical activity forming over the Western Pacific. You have monsoonal flows and thunderstorms over the South China Sea. All of that clouds our ability to see what's actually going on in the lower to middle atmosphere.
So in order to understand how these pollution changes are changing the clouds, we have to actually fly below the satellites and below the high cirrus clouds and look down from the plane and take the plane into various clouds to understand how these processes are changing.
So we can have both points of view. We can actually see what the satellite is seeing, and then we can combine that with what the aircraft is seeing directly underneath the satellite track.
The importance of CAMPEX is for us to study those aerosols and clouds that the satellites can't see. And from what we find here, we're going to be able to validate against the satellite retrievals that we are capturing.
Weather forecasting provided is conducted in different time periods. So we have long-range forecasts that we provide for 3 days, approximately 3 days out or 72 hours. Then we try to provide what we consider a short-term forecast out to about 24 hours. And at the day of the flight, we do an update. And the reason for all this is that the weather in and around the Philippines is very, very difficult to forecast.
When we have a flight day, typically we wake up around 1 a.m. and we make sure that the conditions are looking good for us to complete our mission. You know, if there's bad weather in the region, we might consider delaying takeoff or not flying at all.
If the weather is not appropriate for us to take off in, if the weather is not going to be appropriate for us to land in, or if the weather where we want to sample isn't what we're looking for that day, we can choose to cancel the flight that morning.
It's important to get the right conditions for the aircraft to fly in so they can optimize their sampling strategies.
Generally, we've been giving the go-ahead, but occasionally we have had circumstances where it just was obvious that we weren't going to be able to meet our flight objectives and we could send everybody back to bed. But by 2:30 in the morning, we have to give a go, no-go decision to the entire science team to hop into the buses and come to the airfield and get the airplane going.
The power comes on the plane 3 hours before we take off, and certain instruments have to be in there 3 hours before takeoff to get their instruments calibrated, get their instruments set up and ready to go, and to be, you know, it takes them 3 whole hours just to make sure that the flying laboratory has all of its instruments working.
So to pre-flight the aircraft, we want to get a good look at the entire aircraft from top to bottom to make sure it's ready to go and ready to fly safely for everybody that's going to be on board. So we'll look up in all the flap wells, we'll look at the landing gear, we'll check the brakes, we'll check the lights, we check the props for any leakage or for any for chips or any damage of any kind. We look over the fuselage as a whole. We look for missing pieces, we look for anything cracked or anything just that's going to be unsafe in general.
At that time, I'm in the operations room talking with the pilots and the flight scientists, going over what our mission is today, what we're going to sample.
And we have to tell the pilots, this is the weather you're going to be flying into today, and this is what you need to be aware of when they're actually flying the plane today.
Doors close at about 5:15 in the morning, and the plane is in the air by 6 a.m.
Before takeoff checklist is complete, you are cleared to line up and wait, runway 2.
Up and wait, copy. 1077.
1077.
All right, brakes coming on.
80 knots. Rotate.
So after the plane takes off, I monitor the status of the aircraft, the location, making sure everything is working between ground control and operations on the flight.
The plane stays in the air anywhere from 8 to 9 hours, returning at about 3 o'clock in the afternoon.
And 9-hour flights are quite long, but because we're out there for so long, we can get so many good samples on different clouds. It allows us to really examine the evolution of clouds throughout a day, even with 9-hour flights.
We'll also send up satellite imagery to the flight scientists so they can know where they want to study. You know, they might want to deviate off the course that we planned for them to sample different types of clouds or aerosols.
So we have 2 aircraft in the region. We have the P3, and then we also have the spec incorporated Lear 35.
So the Learjet is basically here to support the NASA P3 aircraft. While the NASA P3 aircraft has a unique set of remote sensors on board, they fly above the clouds or below the clouds, while we fly in the clouds and get the measurements in the clouds, knowing how many droplets there are, how many ice crystals there are, how much water is in the clouds. And this is then compared to the remote sensors, the radars, the LiDARs, microwave radiometers, so that we can interpret the data from in the cloud, where we get the real data, with the remote sensor data, and then understand really what is happening in the cloud, and also being able to then understand what the satellites are measuring.
So after the plane lands, our work isn't over. We have a meeting with the pilots and the flight scientists to see how our mission went and how we need to adapt or change what we did for the future flights.
For the instrument teams, after a flight, they work on shutting down their instruments properly, making sure it's ready for the next flight, and downloading their data. And on some of these instruments, it's quite a lot of data that's produced on a single flight. It's hard drives worth of data produced on a single flight. And downloading that data can take quite a long time.
While the plane is in the air, we're already planning the next flight the following day or the subsequent days. So while the plane is in the air at 9:30 in the morning, we have another weather brief and we start the flight planning process for the next day. As soon as the pilots land, we give them the plan for the very next flight and they file that, and the whole process starts all over again at about 1 in the morning.
Oh man, in total, we're at the airport for about 14 hours every single day and awake for 16. It's a long day.
Everyone is holding it together amazingly well.
So it gets exhausting fast, but it's rewarding.
I work for the ESPO office, which is the Earth Science Project Office, and we focus on managing and organizing field campaigns around the world. Because we start from the ground up all these projects, all these campaigns, we make connections with the local authorities to provide us services for the campaign. So ESPO tends to be the center of the organization of the campaign. So our job during the field campaign is to make sure that the infrastructure is there, and then it's continually, providing the support for the field campaign for the scientists doing the observations. That means that we have to make sure that there's enough infrastructure to support deploying an aircraft in these faraway places. Campaigns like this are very difficult because involve different cultures, different time zones. Daytime's here, it's nighttime back home, so people are away from their families. It's stressful, but everybody's handling really, really well, and it's been a great, successful campaign so far.
Here, no day has been the same. Every day has been different.
So the exciting aspect of fieldwork is that you actually get to see how the data is collected. You're not just sitting at a computer back, at least for me in Illinois, and I don't know how this data was collected.
Some days I'm sitting on a plane dropping dropsondes out of the back of the plane. Some days we're working on the dropson system. Every day is just so different here than what it is at home.
Field campaigns are important for students, not just because they can see where data comes from, but they're going to create friendships that'll last them the rest of their lives.
If any graduate student or scientist has the opportunity to do field work, I highly recommend it.
Being in the field has been an incredible experience as a graduate student. I have learned so much from so many different people. It's been an incredible experience.
We were actually very surprised because a lot of the scientists were giving us praise and were admiring us, were telling us that we're doing a good work, and hearing this from the people that you admire, the people you read on papers, the greats, so to speak, in this field, and then just to hear that from them is really inspiring and makes you want to just do more and pursue more in terms of your career. Yeah.